So let's look more at rotations in Rn and try to get towards a coordinate-free description. It's going to be more elegant and show us better the connections to the triple vector product and to the differential form stuff. So we got into where we discovered that antisymmetric matrices are a really good way to think about rotations, and they definitely are. I don't want to diss them at all. And that the elementary ones would be we can add up, we can express any antisymmetric matrix as a sum of things that look like this, where everything else is 0 except for the -1 and the 1. So I'm calling this the matrix A associated with the pair of vectors EI and EJ, where in the IJ entry there's a -1 and in the JI entry there's a 1. And then the question is, what is A acting on W? Because that's what matrices do. They're linear transformations. They eat vectors. Okay. So if this takes W1, W2 down to Wn, well, it's only going to match up a few things. Okay, so it's going to match up the +1 is going to match up with, because that's the ith column, it's going to match up with whatever's in the ith row here, and so that's going to be Wi. Okay, and then that's going to be spitting it out in the j position. So it's going to be the number Wi times the basis vector EJ. Minus, okay, well, this guy is going to match, I like to picture it kind of rotating in. That's going to match the number in the jth position. But where's it going to show up? It's going to end up showing up in the ith row, or in other words, it's going to be a multiple of EI. Okay, now that might not look familiar yet, but let's write it in terms of a dot product. The Wi, what's a good way to think of Wi as something that comes out of the vector W? It's the dot product of W dotted with EI, and then times EJ. And then this is the dot product of W dot EJ with EI. Ah, now that looks familiar from the rest of the videos in this series. Okay, so here, that's the big clue. Okay, so what we're going to do is we're going to, okay, so given not just basis vectors, we want to get away from this idea that these are special. Given just two vectors, u and v, in Rn, let's define a transformation called T sub uv. Well, let's define a transformation from Rn to itself, which you can think of as an n by n matrix. That's fine. Okay, but I'm trying to get away from the coordinate-based thinking that this matrices lead you into. I just need to tell you what it does on W, and I'm going to define it to be basically the formula that comes out of the triple vector product. So here I'm not so interested in proving this formula one more time. I'm really interested in interpreting what you might be reminded of if you know a lot about rotations. When you see this side of this formula, you might say, hey, I know that that's a great way to define an infinitesimal rotation. Okay? And it's an infinitesimal rotation that's defined by these two vectors u and v. And so it takes a W, and what does it produce? It produces a combination of v and u that's guaranteed to be orthogonal to W itself. Guaranteed to have the nice properties, the antisymmetry properties and the orthogonality properties of that are supposed to be going with an infinitesimal rotation. And then so I'll check that this has all the properties that we want, and then just make some comments about how that makes us think about this formula in ways that are similar to what we had before, but a little different. Okay, so this is pretty cool. The key thing is that this part here only makes sense in 3 dimensions with the crosses, but this makes sense always. Okay, notice I wrote this in a slightly different way. It was with the u cross v in front and the w instead of a cross the quantity b cross c. If you check it out, it's correct. I think I checked the signs, and if I didn't, it doesn't matter really. And I'll talk about why I wrote it in this different way in a little bit. So let's go ahead. Let me clear it out here, and I'll write up that definition again. So T, let's just say T of W, okay, is u dot W v minus v dot W u. The claim is that this is a way to make very elegant the idea that it's pairs of vectors that really label rotations in general. And it's kind of a cheat that only works in 3 dimensions, that you can label a rotation by an axis. Okay, so what do we need to check? So let's see. Is this even a linear transformation? Okay, is this something that if I put W1 plus W2 into this formula, I'll get the sum of the corresponding formulas? Or if I put 2W, will I get 2 times the output? That's pretty easy to check because it's just made of linear operations, the dot product and scalar times vector. So it's just easy exercise with some distributivity laws and some scalar multiplication laws. Okay, so really T is really a linear transformation. Okay, does it have the antisymmetry / sort of orthogonality properties that we saw were crucial to the geometry? Okay, well, it's really easy to check. T of W, that's supposed to be a rotated, W rotated infinitesimally. It's supposed to be orthogonal to W. Well, that's super easy to check. U dot W and then V dot W. Because this is a scalar. Whenever I take scalar times vector and I dot it times another vector, I'm just going to have that scalar coming out times the dot product. Minus, now that's a V, in case you couldn't tell, and then U dot W. Hey, that's definitely 0. Okay, and we know that that's actually enough to check, but we might want to check T of W dot, let's see, what do we need? How about some other one like X? I don't know, I don't like that one for X. Let's say A. Okay, this should be antisymmetric, and these are really equivalent. It's a little bit redundant to do this. V dot A, what I should be getting is something that's antisymmetric if I switch the roles of W and A. That was equivalent. That was kind of the fancier version, what's called the polarized version of the orthogonality. And indeed, I think I did it wrong. Let's see. T of W dot A. Let's see here. U dot A. V dot W. Oh yeah. So is this equal to minus W dot TA? That's actually. Okay. Well, that, if you write it out, that's minus, and so we get T of A is U dot A times V, and then that's going to be dot W, and then V dot A, just plugging in A in here instead of W, U, and then dot W. There we go. And those are indeed in opposite order because of the minus sign. Okay. So this is what we really needed to check, but it's often very nice to know that if you switch where the T goes, you get a minus sign. And that's equivalent, turns out, the matrix language to this guy. Okay. So what the punchline here is that just the beautiful symmetry properties of this combination have a real geometric meaning, and they exactly mean that this guy is a rotation. Okay. So it's a wonderful combination, this wonderful connection between algebra and geometry, that formal algebraic properties like linearity and antisymmetry really have geometric meaning. Okay. Now, let me remind us, I shouldn't have erased it, but let me remind us of the dependence on U and V as well. So I'll write it down one more time. Okay. So we've seen that it has sort of an antisymmetry property in terms of W if we combine it with a dot product, and that's equivalent to the orthogonality. But it's also antisymmetric if I switch the U and V. If I look at the transformation T of UV, I could say, well, what about T of V comma U? Is that something different? It doesn't seem like it should be that different, okay? And in fact, it's just minus of what I get here. So it's not really new information, okay? And in fact, I could have also gotten it by just like negating one of the vectors. That would have been easier, okay? Well, what does this mean? It really means that what I'm doing here is I'm only looking at U wedge V. Now I need to take a minute to talk about how this makes sense. Just the context for these videos, coming out of the differential form videos, if you've watched any of those, we've talked a lot about the wedge of 2-1 forms, okay? But I never actually managed to talk about, never had any incredible reason to talk about, if you have two vectors, it actually makes sense to wedge those together, okay? So, for example, if these are 1 forms, then this is a 2 form. And it's kind of a formal antisymmetric combination of these two 1 forms, and it has somewhat different properties, and it lives in a different place. Well, this is called a 2 vector. It's a formal linear combination of u and v, and it's just subject to rules like if I say instead of u wedge v, I change the order, that's just equal to the negative. And also things like if I say I'm interested in u1 plus u2, and that's wedge v, and then you say, oh no, I'm interested in u1 wedge v plus u2 wedge v, well, those are declared to be the same quantity. So the upshot is that any time you have some function or any kind of machine that depends on 2 vectors and really that it's linear in both of these quantities, which this is definitely linear in the u and v as well as being linear in the w, and it flips sign when you change the order of the 2 things. A really good way to think about that is you really create the wedge product u wedge v first, and then it only depends on that. The picture here is very simple. It corresponds to something we did a lot in the differential form videos. If this is u and this is v, then u wedge v basically is the oriented parallelogram formed by those guys. Okay? And with its area and with its orientation and how it sits in space and everything. So there's actually a very nice picture. Don't have to think of it as a formal algebraic object. So what we're doing here is we're saying to encode a rotation in arbitrary n-dimensional space, what you need is an oriented parallelogram. That its area is going to communicate sort of how much rotation you do, or sort of the speed of rotation, because it's infinitesimal rotation that we're really encoding, and how it sits in space, that it's in this plane and not this plane or this plane. That's going to indicate what kinds of what direction the rotation is going to be in, because it's going to be a combination. The infinitesimal rotation of w is going to end up in the plane spanned by v and u, and the order is going to matter, because otherwise I'll get a minus sign if I switch the order. Okay, so it's a great place where this bivector or 2-vector idea comes in. Okay, so with that little bit more sophistication, instead of saying it's pairs of vectors that label rotations, it's really that we're getting a correspondence here between the set of all rotations and the set of all 2 vectors, which geometrically could be thought of as oriented parallelograms. And remember something that I talked about when we're talking about an interior product. If you say, oh, I'm interested in this parallelogram, like it's a rectangle with this orientation, and then somebody else says, oh no, I'm interested in this parallelogram, it's not even a rectangle anymore with this orientation. As long as the orientations match, counterclockwise, counterclockwise, and as long as they're in the same plane, and as long as the area of one is equal to the area of the other, then we really are talking about the same thing. They're built out of vectors in a kind of a different way, but they're really the same quantity. Okay, so this would be, if this is like u wedge v, and this is like w wedge z, then they can still be the same thing, even if u and w are not the same, or v and z are not the same. So it's just basically little oriented bits of area in a plane, I guess would be a better way to say it, not focusing so much on exactly the edges or corners of the parallelogram. So the claim is that that's exactly the general way to label rotations. Okay, and I've told you the mapping going this way. You give me the u and v, and we create that triple vector product formula, and that'll create the rotation. It's easy to see that this is a one-to-one correspondence just by looking at the basis version again. A, E, I, E, J. We know that any rotation is a combination of these guys, and any 2 vector is definitely a combination of just EI wedge EJ. So we'll finish this up next time.